This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
All right. Okay, let's get underway. Right. I want to finish off quantitative analysis very quickly. We were learning that there's a lot of doom and gloom in trying to measure, in particular, worst case execution time of programs on embedded systems. It's not all that bad, and I'll show you some ways that we are combating that in embedded systems land. Then we'll talk about security and privacy, which is a massive area of cyber physical systems or embedded systems that has been under-addressed for a long time and could cause things to blow up, literally, sometime soon. So if you had a fragment of code, if you recall, we wanted to basically work out the worst case of executing it in terms of the time it takes to do so. And if you have timing information on blocks of code and you know how many times they run, you can kind of set up a linear integer programming problem in order to try and work out the maximum time by maximising that quantity there. Now, unfortunately, it doesn't quite work so nicely. So if we did that for a particular task, maybe a function in C, and that was task A, and we did the same thing for task B, another function, and they are sequential operations, so A happens first and B happens afterwards, the overall composition of those two things, in general, WCET, the worst case execution time of those two things, is not the sum of them individually. Okay? Why? Well, there may be dependencies through environment that happen. When we're thinking environment, we're thinking the embedded environment. So architecture, cache, memory, maybe sensors, interrupts, all that sort of stuff can interfere with this, and it's not necessarily simply an additive thing where you can add the two things together. So not always. It can happen if they're largely independent things on a simple system. Yes, but not in general. Now, so how do you actually go and measure these things? There are a few ways of doing it, ranging from the simple, or the easy, to the sublime, basically. First method, which is fairly common, is to basically be sampling the CPU cycle counter. So in the microprocessor, you've got a cycle counter, and you can be having a look at what it says every once in a while. Knowing the clock rate of the processor, you can then obviously convert cycles to time and work out how long something's taken to do. And that's pretty easy to do. You can just go and look up the documentation for the processor and find the assembly instructions to do that. Now, you've got to do it in assembler, or you should be doing it in assembler, because if you're doing it in C, you don't know how that code is going to necessarily translate to assembler, and therefore it may not be an accurate representation of what's actually happening in the processor. More about that in a minute. Two other ways, which are, well, the second one is used and the third one is not used so much. But the second way is then to do it all in software. So if you have some super accurate simulator that is cycle accurate, and you don't have the hardware sitting there ready to go, you can obviously simulate your code on a virtual processor, and that can give you some information about the timing of such things. Once again, then if you don't have an accurate model of the environment there, then things may not necessarily match reality. And the last one, which I'm sure you wouldn't want to do, is to get a logic analyzer in on there on the pins, right? For instance, of the CPU. So something to measure the physical values of what's going on inside the pins there. It's non-intrusive, so right, you can just get it on there. And it's more accurate, but it's obviously very difficult to do. You have to have the hardware, you have to get in there. If the pins are very difficult to get to, you might not be able to get them. To them. So typically you can have test points on circuits. So you've got a processor with a few hundred pins, maybe, I don't know, 500 or 600 pins. They're ball grid arrays, so they're underneath it. It's a 6-layer board, so you've got no chance of getting in underneath to sample the pins, right, to measure when instructions are finished. You might be doing that in the code, toggling a pin maybe or something like that. You run tracks out to other areas on the board with test points or headers where you can connect into nice and easily. And you'll see that on a lot of boards. Even in production, they still sometimes maintain those tracks there with the test points, either for servicing or they can't be bothered removing them for the final production of a particular circuit. So this instrumentation code, so just going back to the first point here, this instrument code, it incurs a small overhead, right? So if you are, go back to that first point again, sampling the CPU counter occasionally to count how many cycles something's taken, you are interacting with the environment yourself by issuing those operations. So you, by running operations or instructions to do that, are affecting the timing. All right, but what you can do is you can get around that by, if you measure the timing for a large sequence of instructions, your overhead of measuring, capturing the CPU cycle counter and capturing it at the end is small relative to the amount of time you're measuring. But there are issues. If you're doing a big piece of code and halfway through multitasking occurs and you do a context switch and then you come back and you measure the time, you may have had no idea that that context switch has happened and you're measuring a time that's inaccurate, getting from here to here. Okay? So what you could do is you could do a cluster style measurement. So you take a range, you do that many times and you'll see some outliers perhaps where their context switch is happening, and then take averages and all sorts of things, or the k-best times or something like that. Once again, multi-cores, that makes things really messy as well, because you may, other cores may be doing other things, so you need to lock a particular task to a single core in order to accurately measure how long something's going to take. And then, another big thing in IoT or embedded situations, power management effects. So typically, the CPU, for smart sort of systems, the CPU can ramp up and ramp down its clock speed in order to save power. And that complicates things because that happens dynamically. You can do it user programmed, but it also can do it itself on the fly. So it becomes difficult there when obviously clock speeds are changing and you're trying to measure some accurate timing between point A and point B. It gets very messy there. In addition, I should also say, if the processor decides to go to sleep in the middle of a task that you're trying to measure the timing for, or some elements are turned off, like timers and things like that, you may get garbage in there. So you read out a timer value and it comes up as garbage, particularly when it goes to sleep or into hibernation mode. Oh, it sounds all bad news. But, and the reason is because processors are getting more and more complex. In the 80s and even in the 90s, processors were so simple. Single thread, single core, very structured and simple memory arrangements, and now we've got crazy caching, we've got multi-cores, etc., right? And threaded programs as well, and OSs that can do all that sort of stuff. So we've got two questions. Can we create processor models without all this pain, to have to model all of this? Yes, and the answer is, how do we do it? Well, the big thing that's going to do it is machine learning. Okay? To use machine learning to basically predict the processor's behaviour and therefore get an accurate model of the processor, rather than explicitly trying to come up with a model for it. You can then just use machine learning to let it train itself and work out what the model is itself. Or can you flip it and say, maybe it's the architecture that's the problem. We are trying to time an architecture that's almost untimable. So how about we change the architecture to start from the premise that the timing is important? And so the answer to that is also yes. So if you want to read in the book, and you can see this online, there's the PRET project. And PRET's an acronym there. And that's a project that looks at trying to determine an architecture which gives you reliable timing estimates on tasks and things like that, okay, which is important for embedded systems. At the moment, all our analysis methods are terrible. Brittle is the nice word to say, because if you change small changes to your code, or just change your architecture, double your cache or something like that, or something very simple like that, means that all of that pain that you went through to calculate these worst case execution time has to be redone again. Okay, and it might mean lots of simulations, logic analyzer, whatever you need to do to regenerate all that data to get WCAT times. That's to do with machine learning there, right? So we could learn about processor platform behaviour via machine learning. All right, so the summary of all of this is, it's a tough area. It's sort of a 20, 25 year open problem, this, and there's a lot of active research in this area, and that's the takeaway message. We need more accurate ways of measuring execution times. If we tackle it from trying to use really advanced stuff like machine learning to get processor models to then simulate, or we tackle it the other way and say, let's make hardware that can make timing analysis easier. And there's the two branches that are tackling this. Okay, so it's not all bad. I encourage you, if you're interested in this sort of stuff, Google this sort of stuff. There's lots of research papers, there's lots of survey papers out there that can get you started in this area. And it's an active R&D area for a lot of the large embedded companies that are out there too. All right. So what I'd like to do is I'd like to follow up quantitative analysis, which we realise is difficult, with something that is also difficult and is going to cause a lot of problems. Security and privacy with respect to embedded systems. Now, before we embark down this path, I have to make a disclaimer to say that I'm going to discuss some things that are vulnerabilities in systems. And so therefore, it gives you no excuse to go and try these things out, basically, in order to create havoc with such things. And I've got personal stories I can tell you about, again, where I did such things, but I don't want you to replicate it, okay? But we still need to talk about it because it's interesting. Okay, so I'm just putting that out there. Don't go and do anything illegal, please, in the IoT world, even if there's a security hole you can see. So what I want to do is I want to try and formulate what the threats are out there in terms of IoT, how we can get around it, and encryption is the big, simple solution, but there are also big issues when it comes to IoT with that, or embedded systems. And then look at sensor attacks, which are the scary ones in my mind. So I've got this little picture here that shows, remember, CPS is an acronym, another acronym for an embedded system. It's, you know, cyber physical system. And if the cyber part is in the bottom here, it's all interconnected, and the physical part at the top there, they can be interconnected as well in terms of, you know, some sort of sensor network, and also the connections that are jumping domains between cyber and physical. So you've got connections here, and they're the main ones we're going to focus on, but you could also have interplay between the the physical things themselves. Okay, so we're going to focus on those two arrows I drew first. How do you get security and privacy going this way, from the physical to the cyber domain and within the cyber domain? Now, you can neatly model all of the threats and everything according to this 3D cube here along 3 axes. And the 3 axes represent disclosure, so that's some sort of measurement of privacy, disruption, and that's obviously an artifact of something bad happening, and having knowledge of the system. Now, that's probably the one that people don't think necessarily about, but having information about the system is almost as important as being able to get in there itself, having a model of what the system does. So you can plot all the bad things that can happen in IoT world on these axes. For instance, someone eavesdropping, right, and stealing information. That's basically just along the disclosure axis there. A denial of service attack, so flooding some server somewhere or a resource with spurious requests and meaning no one else can connect, that goes along the disruption axis. But then you've got ones that combine both elements or 3 elements. For instance, a replay attack, where you can basically capture data, so it's the disclosure bit, and then attack something with that particular data set. So denial of service combined with legit information. If you know something about a model of the system, you can do either bias injection attacks or zero dynamics attacks. And if we notice, you need more knowledge of the model to go to the zero dynamics attack. I'll show you an example of the zero dynamics attack and the bias injection attack actually in this lecture. And that's essentially where, if you know a bit about the system, you can spoof things in the system and cause havoc, basically, because you know a bit about the model. You know perhaps how it's supposed to respond. You can spoof sensor data in particular and really screw things up. And the worst one is probably this one right here, and that's in 3D. So that's coming out of the page at you. That's on all 3 axes, and that's where you have knowledge of the model, knowledge of some sort of privacy aspect of it, and then also you're able to disrupt it in some way and remain undetected. And that's the really scary one. All right, so if you want more scare stories, it might be hard to see, but if you plot the amount of attacks that happened, so that's vulnerabilities here, versus the area where they happened in, the things that are being attacked are big, important things. Energy, critical manufacturing, commercial facilities, water, like serious infrastructure things. These aren't people's, you know, PlayStations or something getting hacked, right? These are serious systems. And there's a bit of a timeline here showing things ramping up. If you remember, you may have heard of Stuxnet, which attacked a particular type of control system, a Siemens control system, and essentially screwed up Iran's nuclear facility for some time. because they basically, the centrifuges shook themselves to death or something like that. German steel mill got hacked and a blast furnace got blown up. Ukraine power grid attacked. There was a big power outage. This is maybe a test of concept sort of thing. And then the Norsk Hydro, which is just this year, and I'll put a link in the slides here, in just a quarter of a year it cost 52 million bucks. I think it was about 75 for the half year. So how do these things happen? Oh, whoops, I forgot there's an animation here. Sorry, I just have to pop it back onto here. Damn animation. So underneath the animation is this. So this was a sort of a schematic representation of what happened in that Ukrainian power hack. Some nefarious attacker came along here and had some information about the system that they were going to attack, right, in particular. They did 2 levels of attack. So you've got to get some sort of malicious code in particular into a system, and the easy way to do that is via mail, because people who read email are generally pretty dumb and they just click on things and open stuff. And secondly, a distributed denial of service attack for the workers. So simultaneously you are infecting a system, cutting the power and causing damage as well via this SCADA type interface. That's a control system, basically, an industrial control system. That caused the outage. It also blinded the network so they couldn't see what was going on, and they put all sorts of weird stuff going on in here, but in particular a secondary attack that saturated the support people and stuff, so, and the technicians, so they're all busy trying to put out a fire or answering weird phone calls and stuff when the real stuff is happening behind them and they don't see it, okay? And the outcome of all that was, you know, tens of thousands of people lost their power for a bit. Okay, so that's a targeted attack. Obviously, someone knew what they were doing. They had particular code that would be amenable to these SCADA systems. The scarier one, I think, is the Mirai IoT botnet. And this started out as someone essentially wanting to do a distributed denial of service attack, so take over a lot of computers and attack servers. And the guy, they think the guy that came up with it was motivated by Minecraft, funnily enough, that he didn't like Minecraft servers that would rival the server he was running because you get money based on the amount of people on your servers, so he just wanted to slam all the other people's servers. So he released it, and, well, they think it's a he, but yeah, anyway, released it, and hundreds of thousands of things got affected, and the US, large areas of the US internet just dropped out, which is crazy. So there's the source code there, attack, I love that. Function attack, no arguments. And it just spans over a range of stuff. Now, so what happened was Linux machines, now you might think Linux, who cares, it's just Linux. A lot of servers run Linux and a lot of IoT devices run Linux. Got taken over as bots and then basically contacted other ones. How it did it was fairly simply. This is the source code for it. So what it did was it basically just attacked Telnet port. So Telnet is a particular port. You can log into a device and get command level access to it, command line access. What it did was it basically spanned through, I think, 61 generic logins. As we'll see on the next slide, unfortunately, with IoT, most people don't bother changing the default password or username because they just think, oh, well, it's just, who cares? No one's going to sit there and try and log in. So it ran through combinations like all of these things. You can see there's some pretty simple ones, admin and password, or root and none. I mean, yeah, well, they tried it. And if it got in, basically, then it would then install some code and then replicate itself outwards, right? And then at a preordained signal could do a distributed denial of service attack from lots of areas onto one target. A guy who is actually a vulnerability expert, his site got hacked, not hacked, attacked by this bot here. Now you might think Linux, big deal. Linux, I don't have a Windows machine at home or a Mac, I don't care. The scary thing is This is some of the source code for it, and the source code's available on GitHub if you want to go and look it up. These are the compile options for it if you've compiled C programs. If you look in that column there, they're all the architectures that it is compiling for. So MIPS machines, ARM-based machines, so embedded systems normally, PowerPC, that's a bit old, but Spark processors. Wow, these are not Windows machines and stuff. These are things that might be routers. Routers typically run ARM processors with Linux OSs on them. CCTV systems. Yep, the cameras themselves, the firmware on them normally runs, it has an ARM chip on there that runs the show, and people normally don't change the passwords and stuff on them. So, yeah, if you want to have a look what happened over time, right, these are scan packets that were detected by UMichigan. Bang, you got this massive spike of packets detected of the Mirai scan packets. Almost 1 million devices got infected, and unfortunately it's getting smarter. That was only trying 61 possible user password combinations. Now that it's up there on GitHub, people have taken it and modified it and had more scanning going on and stuff like that. So obviously it could potentially get worse unless people lock down their systems. So some other interesting examples. We saw Stuxnet. A very interesting one was the traffic lights in Ann Arbor in Michigan were attacked in 2014 on purpose by a hacker to show how easy it was to get into the system. Now, traffic lights, when they were invented, they were standalone units, right? You would build a little state machine for your little intersection with your pedestrian crossing and maybe a train crossing or something. And as things evolved, they started to get networked to improve traffic flow. And the networking part kind of happened without thinking about what would happen if someone got in there and were able to get onto the network of these things. So to give you a really brief flyover of this, and I urge you, if you're really interested, read this paper. It's very high level. There's no maths and stuff in it. It's really interesting. These things basically locally talk to each other over 5.8 gigahertz. You're thinking, oh, hang on, that's like a Wi-Fi sort of frequency. Yes. And they also then talk to adjacent devices by 900 megahertz signals, right? Lower frequency goes a bit further. What happened is these things talk via the 5.8 gigahertz. Now, the people who implemented the communication between the lights said, we'll implement a proprietary protocol. So if you sit there with your laptop, you can see these things have SSIDs, right? So you can see the SSID, but you can't log into it because the computer can't log in via, it doesn't recognise the protocol that these things are using. So it's a proprietary protocol, but easy. You can go and buy the radio receivers for these things online and plug it into a computer, you know, as a development board, and there you've got access, right? Because it was a proprietary protocol for talking with these things, they basically left no security on them. They just thought, oh, well, someone's got to go out of their way to get the hardware, so who cares? And essentially, all the communications between these is unencrypted, so you can see exactly what's being sent between them. And to log into the controller that runs these things, which is, you know, located in a box or something, there's no username or password on it. Right? The security is, oh, well, someone has to go and get a radio card. That's the security. Anyway, so these people basically showed that they could do several things to the lights, right? They could make them all green, right, which is dangerous, and then they could monkey around with them, right? Make them flash really quickly and stuff like that to confuse motorists. What was even worse was these talk via 900 megahertz to the adjacent ones here. And they found that, once again, you could also hack that signal. It was unencrypted, there was no username or login, and you could therefore spoof this intersection. Without controlling these lights, you could spoof what this was supposed to be sending to the one across here. Now, they implemented some very basic security. a 16-bit code. You think 16-bit, that's a lot of combinations. So for instance, this one over here would be waiting for the 16-bit code of this and would only accept data from this if it recognised the 16-bit code. So you would have hard-coded 16-bit codes in these things. So now what happened was there's not many lights that can communicate over 900 megahertz with each other. So out of those 16-bit numbers, which is about 65,000, if you wanted to try and hack into you have to enumerate over all of those possibilities. It'd take you a while to cycle through them all to try and get a response, right? Unfortunately, what they did was they started at 0, right? And they wouldn't encode more than 100 numbers that start again because you wouldn't have more than 100 within the range of a cluster of these things. So in essence, to find that ID, instead of going over 16-bit numbers, you only essentially went over less than 100. So it was pretty easy to just run over them, hit something that got a response, or you could decode the data and then you're in, which is, once again, damn scary. And because the people thought, well, you know, if someone's got a radio, custom radio to get in here, then that's the security. No one's going to do that, which is dangerous because, yeah, you easily can. So this is a nice comparison of the two things. So on your desktop or mobile, security has been around for, you know, since the turn of the century, so to speak. In about 2001, Bluetooth was taking off. People started realising that network is evil and it wants to kill you all the time. So start locking it down, right? Stop stuff getting in, track stuff. So lots of security investments going on. Now here's the interesting one. The OS, the platform and the browser vendors basically actively manage your security for you. You sit back and let Microsoft do the updates or Apple do the updates and it's all done for you. You don't need to do anything. Automatic updates applied. Defaults assume users are uninformed, right? Because only idiots use computers and stuff, so you've got to lock everything down and the developers look after you. And also, there's only a small number of popular homogeneous platforms to protect. You know, you've got your Apple ecosystem or maybe your Windows ecosystem. That's about it. So what happened? Well, in the IoT world, everything on the left is essentially inverted. People still don't believe that the network's bad and wants to kill you. There's a massive underinvestment in security. Basically, it's either an obstacle, because IoT stuff, it's hard to do security for low power, so someone else's problem, like in the traffic light controller, basically. It's like, oh, well, we don't really need to do it. Or consumers have to manage the security themselves. What that means is no one does it, right? If the onus is put onto you, you don't do it, right? And that means that people don't update stuff. When was the last time you updated the firmware of one of the devices in your house? Probably never, right? And any defaults essentially just throw the users to the wolves, okay? So if you don't lock things down, it's their own fault. And I'll give you an example of that. When Bluetooth came out, when it was getting more widespread in phones around this era, I found an exploit on phones, right? On a particular phone with a particular operating system, what you could do was you could essentially send a contact, so, you know, a contact in your address book, to that person without them accepting the contact. So they will just get a contact appear in their phone, right? So my pet project was going out to shopping centres. Sitting in the food court was the best place because you could see everyone on their phones or looking at their phones, and you'd find that particular model, and then you'd do a scan of all the IDs, and everyone was broadcasting Bluetooth back then. You were always actively scanning. So you'd look and you see a male and you go, okay, it's probably Ben, that guy, Ben's phone. All right, cool. And you'd send him a contact, right? And you would send, yeah, you would put funny names. I'll just say you put rude names in the contacts and funny numbers or friends' numbers and stuff like that. And one of two things happened. Either it came up with a notification and told them that something was contacting them, and if that happened, you would basically put "I'm watching you" or something, and it would come up as a contact, "I'm watching you," and then you'd look for the reaction, or it would just do nothing, and then it would update it in the contact book in the background, and then when they get home, they'd be looking through the numbers and going, "What the hell? What number's that?" And they would never know. So that's a perfect example of what was happening on the mobile situation. Default settings were Bluetooth broadcasting all the time and accept anything that comes in and tries to connect to you for that operating system. They were fun days, though, I have to say. IoT is a problem as well. You've got so many different devices. How do you apply some sort of blanket security to them? You essentially can't, right? It's very difficult to do. So, I'll give you a little example that violates a couple of these things here, but these are just questions that have to be asked. So, confidentiality, so is there information that can be gleaned from the sensors, in particular sensors? Can you get integrity, so can the system get in there and start modifying stuff? Can you be communicating with someone you're not supposed to be communicating with? And can you, is the system basically being crippled in some way? This is another scary example. So if you know anyone that has a pacemaker device, a device that regulates rhythm of the heart, beating of the heart, these things are a IoT security threat, basically. So back in 2008, a study was done on pacemakers. How you program them, there's actually a radio programmer that can program them. The doctor can do that, or surgeon or whatever. And you can actually attack them three ways. If you have your own programmer, if you listen in on the comms, so you're in the room next door and you're listening to the comms that come from the device the doctor has and the patient, you can actually read very sensitive data from that. Or, even worse, you can eavesdrop, get information about the system and then generate arbitrary RF traffic and spoof the programmer. So there are three things that you could do. The commercial programmer can do everything. If you're just eavesdropping, you can actually work out if they've got one installed, but you can also then pull serial numbers and telemetry data and all sorts of stuff, and then maybe even get patient history stuff out of there, which is scary. The worst one is obviously if you can generate arbitrary RF traffic, you can do integrity things. So you can change the settings, or the worst one, deliver shock commands remotely. That's scary. There's almost no security on these things. Why? People just think, who's going to do that? But it can be done, right? So how do we get around such things? Well, the privacy part is pretty simple. I'm not going to go into detail about this because you can read up on it, and it's interesting, but cryptography is the way to go. So if you just encrypt everything, that's easy, then no one can read what you're doing. No one can spoof the data because they don't know how it's encrypted. They don't know the underlying data structure because it's all encrypted. Sure, that can work. So the simple solution for that was to have what are called one-time pads. So in a pre-IoT days, you had a password, someone knew your password, or a key, let's say, someone knew the key, and you could communicate with that key. But that would mean you have to walk along and give that person the key, and you'd have to have a copy of it yourself. And how it worked was it'd be just on basic logic. Given a message and a key, you can generate the code by XORing the key and the message. Now, XOR has a beautiful function that property that's associative and commutative, if you remember back to your old logic rules, and when you XOR something with itself, it's 0, and that when we XOR 0 with something, it also returns itself. So what that does is it has some really nice properties that if you get the coded message, you can just XOR it with the key and you get back the message by those properties. So it's really easy. Both of you got the key, send the message, XOR it, you get your message, get your decoded message back. And it was nice that even knowing C, so even if you could steal that message, there's no way that you could get M out of it, basically, with the properties of the XOR, right? There's no way you could get info out of it. That's all that says. But the problem with this is the more you use the key, the riskier it gets. If you encode two messages with the same key and then someone steals those two messages, they can do some operations on them to recover a little bit of information about the messages. They can do some more advanced analysis on these messages, and you know, maybe if you're always saying hi as the first part of the message and you now have got two messages both encoded the same way, maybe you could do something, but you've got the XOR combination of the two. And obviously the more that you do send with the same key, the worse it gets, the more information they can build up about the message and possibly break it. So what happened then? So then it got more complex, using block ciphers. So key size and message size don't have to be the same. You use you encrypt different ciphertext for the same messages, and it led through sort of 30 years of development to AES, which was the encryption system that came out around the turn of the century. And it uses all these different key lengths, and it's quite involved. But it still requires you to know each other's key. And so that was okay perhaps before the internet. Then what happened? Asymmetric public key cryptography came along. In other words, basically RSA. And I'll talk a little bit about RSA. So the idea is that if you are interacting with an entity that you want to do encryption with, but you can't walk over to their house or their server and swap keys, right? How do you do that? And you can't send them the key because that could just get intercepted. You use private and public keys. The idea is you encrypt your message with a public key, and the message can only be decrypted with the private key. And the public and private keys have very special algorithms involving prime numbers, which make them hard to pull apart, basically. And this is what's called a one-way function. So I'm not going to go into huge detail about this. The algorithm is here. Once again, I don't care about you knowing this, but it's there for those who are interested. You generate an encrypted code based on the properties of these numbers. Let's not even worry about that, to be honest. And what that did was, so think about how this is growing. The encryption and stuff is now taking off. You've now got asymmetric keys and stuff. IoT is still not yet really born, right? So it's a long way behind the internet and encryption and stuff. Then SSL, right? The example of asymmetric cryptography. So if you view HTTPS, you're using SSL or TLS, and you get authentication. So this is essentially how it works. This is without certificates, I should say. So you've got a browser client, and you need to encrypt the following things. You've got to encrypt the ID and the password to get into the system, to log into your unique account, and you've got to encrypt information coming from the bank, like the balance, and then directions from the browser, like transfer some money to some account in Nigeria, right? So you've got to be careful here. This all has to be encrypted because the internet's a bad place and you've got the naughty man that can eavesdrop. So here's the idea. So this doesn't work, right? Because in order to have a shared key here, the one-time pad, for instance, how would that key come to you? Maybe it could come physically in the mail or something, but even that could be intercepted by someone, right? Just look in your mailbox. So this is the way that the RSA works. Everyone has private and public keys, and the bank essentially sends you their public key. You encrypt what you want with their public key, and then they decrypt it with their private key. Just keeping it really simple here, right? You can look into the maths of all of this on the previous slides here. And that's beautiful, right? Because you don't need to pre-share anything, any secret keys or anything, and you can do it all on the fly, interacting with someone for the first time, right, who has a public and private key. But there's a problem. So Now think about, this is all internet stuff, right? So think about, this is internet, and IoT is starting to now grow, right, as this stuff is taking off. But there can be Malcolm in the middle, Mallory in the middle, right, sitting there, who's nefarious. And what he does is he spoofs network address. So it doesn't go to Bank of America, but via DNS cache poisoning, for instance, it points to his little server somewhere, sitting somewhere. Now, classic example of this is never, ever use free Wi-Fi spots, right, for sensitive stuff, particularly in hotels, because there are people who pop up their own hotspots to be this guy in the middle that are open access and look like the hotel Wi-Fi hotspot. Yeah, be very careful. Anyway, so this guy pops up and he says, that's the real Bank of America address, because he's poisoned the DNS cache in the system, and therefore he now acts like the bank to the browser, the person, the client, because he sends his public key across that's encrypted with the public key, and then he decrypts it with his private key, does whatever he wants to it, and then performs that same transaction with the real bank. So he just then pretends to be the client, basically. So that guy's pretending to be the bank, and he's also pretending to be you on the other side. Okay, so how did all this get solved? So this was a perfect solution, but once again, we misunderstand that humans can be pretty naughty. So how do we solve that? We solve that via certificates. So there's a third party now involved, and I can't draw on this computer. So up here you could draw a third party now that issues trust certificates to corporations, and the trust certificates are built into your browser. So there's a third party involved that is verifying certificates from websites against a known list here that can then basically prove that that's the real person that you're dealing, or thing that you're dealing with. Wow. So all of this is great for PCs and infrastructure and all of this, but for IoT, there's not even encryption in a lot of places, let alone public-private key stuff, let alone trusting certificates. You can't get a trust certificate for a temperature sensor, right, sitting in a room somewhere, right? So all this stuff is widely used on internet, but not on IoT stuff or embedded systems. So how do we do it? It's still an open question about how we just set up the networks for these such things. I want to just quickly talk a little bit about sensor attacks. So that's security, and I'll say IoT once again almost has no security. Everything's like default password and easily getting into. So software security. The problem with software security with embedded systems is typically you don't have an OS there that can run a virus checker or malware detector to find something bad going on, or a hypervisor, so some sort of terminal you can log into and see stuff happening. Typically these are headless systems that are just running in the background, and the only way you know something's wrong is you get a huge bill for something, right? Or something explodes or catches fire or something like that, right? There's no way of knowing something bad is happening. So software security is even more paramount for IoT systems, because you have almost no feedback that something is gone wrong. I'll give you another example, sensor attacks. And this is a huge problem for IoT or embedded systems. Okay, so sensors, one of the reasons why all this crazy overhead here just to talk to your bank is not implemented in IoT is why? Well, it's not clear. The network that you're dealing with may be just a very local network, right, where you just got sensors talking to some control unit in the building, right? There is maybe even no internet access. So there's no concept of trust certificates and all that sort of stuff going on. Even worse, implementing all this rubbish costs a lot of power. And you've got little battery devices that are up high monitoring the temperature in here. You don't want to get up and change them all the time, right? So that's why that's not implemented. So what about sensor attack? So easy. Sensor attack. you can capture sensor data, manipulate it, and output it either wrong values or hold on to it and output it at weird times and throw a system, right? So if you fail to detect such things, right, bad things happen, right? Computers, who cares? You lose $1,000 or something, the bank gives you the money back. But bad things happen in IoT world because an actuator does something it shouldn't do, and there goes the power station, right? Here's an interesting representative example. Don't try this at home. If you've ever pulled the wheel off a car and you've seen this funny gear thing here, it's not a gear. I thought it was a gear years ago when I pulled a wheel off my car. It's a tone wheel. It's called a tone wheel, or tone ring actually. And what it is it's just a bunch of notches that, when going past this sensor here via Hall effect or such magnetic property here, right, it can detect the speed of the wheel, right, because it gets pulses and such, right? So via these teeth, if you like. And that's an ABS sensor. So if you've ever had a look on a wheel, you get it, that'll be under there for sure. So there's a permanent magnet here, and then you've got the tone ring. When the wheel rotates, the tone ring, you know, you've got bumps and grooves or whatever, it generates a magnetic field, pulsing magnetic field. You can determine the wheel speed from that. So what you can do? Well, you can implement a sensor, a non-invasive sensor, so you're not cutting wires or anything, that can essentially see that magnetic field there, cancel it out, and inject a new magnetic wave to completely spoof the sensor. So you're cancelling it and injecting something. So that's, on that cube of things, that's way up there. That's a bad one, right? Because you are not cutting things, so you could remove this and you are spoofing the sensor data. So what's the result of that? So here, this is over a 2-second period here. This is the wheel speed, and obviously, you know, it's got noise and stuff, it varies a bit. And in this paper here, it showed that you can basically inject, and this is, the blue is the compensated spoofed wheel speed here. So this is just like linearly increasing, right? So it was going at a relatively constant velocity with a bit of noise on there, but this here is showing that it's accelerating, which is the car is clearly not doing. Okay, so it's been attacked. And what's the outcome of the attack? This is a nice demo of what happens. So ABS is to stop the brakes from locking up, right? So if you're driving on ice, which we don't really get here, and you immediately move to the right to get off the ice, right, the ABS will detect if the wheels are skidding and pulse the brakes to stop that. Now, that little system was put on that car with the left rear ABS sensor. What it did was it reported a lower velocity, like in that picture, than the true wheel velocity. And what happens? So what's the simulated effect? You're on the ice, you move off the ice, it says the wheel speed's going slower than it really is, and the car loses control and crashes, basically. Well, it didn't crash there, unfortunately. There's no tree. But simple, right? How do you stop that? How the heck do you stop that? There's no encryption. That's just spoofing a magnetic field. Yikes. How do you stop that? Now, in computer world, how we do that is we do challenge response authentication, right? So you issue a challenge and get the response. So you could think of, you know, username, password sort of thing, or you could say capture codes, stuff like that, right? How many traffic lights are in this picture? That's a challenge response kind of thing, right? This is really interesting. In the cyber physical world, you can leverage the fact that you have physical devices in the system that are governed by physics. So what you can do is you can put impulses on the system in some way, affect the system, and then read back what the sensor data is saying, right? Because the physics can't lie. So you can read about it here, but in our little ABS example, you're driving along. Let's say the computer thinks, the ECU thinks it's being hacked, right? what it could do is it might be able to actuate the brakes just a little bit, right? Just actuate them. And if it doesn't see a corresponding decrease in the wheel speed, and it would know from the internal model of what the car, dynamics of the car, how that should decrease, but it sees it's still increasing, it'll go, whoa, failure. Either failure or it's been hacked. So the challenge is comes in a physical stimulus, like pulsing the brakes, or maybe even imperceptibly, and then reading the response and